On a flat, calm sea in the South China Sea, scientists watched their instruments suddenly spike. Monstrous walls of water, nearly 500 meters tall, surged through the ocean's depths, entirely invisible to the human eye. These skyscraper-sized internal waves shape climate, threaten submarines, and move energy across continents. Yet only satellites can trace their ghostly footprints. How can such giants remain hidden, and why does the world depend on their secrets? Internal waves in the South China Sea reach dimensions that almost defy belief. Instruments anchored to the sea floor have traced these underwater giants as they rise and fall through the water column, recording vertical displacements close to 500 meters, taller than the Empire State Building. Yet above these skyscraper waves, the sea can appear perfectly calm, betraying none of the drama unfolding below. Scientists tracking the life cycle of these waves west of the Luzon Strait have documented their full journey, from birth to breaking. As each wave approaches the continental slope, it grows steeper and more powerful, eventually collapsing in a burst of turbulence. Measurements taken during these breaking events reveal a surge in energy. Turbulence levels spike by factors of 10,000 compared to the open ocean. This turbulence is not just a statistical oddity, it is a physical force strong enough to mix heat, salt, and nutrients across layers that would otherwise remain isolated. For marine life, these mixing events can shape entire ecosystems, fueling plankton blooms and supporting rich fisheries along the coast. For engineers and navigators, the same turbulence poses a challenge, as sudden invisible currents can test the limits of submersibles and moored equipment. The South China Sea stands out as the most energetic internal wave environment yet measured, with daily displays of underwater power that remain hidden from view unless you know exactly where and how to look. The sheer scale and energy of these waves demand a new way of thinking about the ocean's interior, where calm at the surface can mask a world in motion hundreds of meters deep. Inside the ocean, water is stacked in layers according to density. Warm, lighter water floats above colder, denser water, creating a boundary known as the pycnocline. This boundary acts like an invisible sheet stretched across the ocean's depths, flexible but resistant to mixing. Internal waves travel along this pycnocline, sometimes shifting it up or down by hundreds of meters. The remarkable part is that while the pycnocline heaves and dips deep below, the sea surface above barely stirs. The reason lies in the physics of density. The contrast between air and water at the surface is huge, so even a small disturbance makes waves and splashes. But within the ocean, the difference between layers is subtle. When an internal wave pushes on the pycnocline, most of the motion is absorbed inside, and only a tiny fraction reaches the surface, often just a few centimeters, easily lost amid normal wind and chop. Instruments anchored in the depths might record a vertical swing of 200 or 500 meters, yet a person on deck sees nothing but calm water. This is why internal waves are so often missed by the naked eye. Their true size is measured not by the height of a crest above the water, but by how much they displace the density layers below. The pycnocline acts as both a pathway and a shield, letting these waves move unseen across entire ocean basins. Understanding this hidden motion is the key to seeing how something so enormous can pass beneath a boat without leaving a trace on the surface. Far above the ocean, satellites scan the sea's surface for clues invisible to the human eye. Synthetic aperture radar, called SAR, has become the tool of choice for tracking the hidden giants below. When an internal wave passes through the ocean's interior, it sets off a chain reaction that reaches all the way to the surface. The motion of water along density layers generates horizontal currents, some pushing water together, others pulling it apart. Where these currents converge, natural slicks and surface films accumulate, smoothing out the tiny wind-driven ripples. These smooth zones appear as dark, glassy lines in SAR images. In contrast, areas where water diverges become rougher, scattering radar signals and creating bright bands. The result is a striking pattern, alternating ribbons of dark and bright that trace the crests and troughs of the internal waves, sometimes stretching for tens or even hundreds of kilometers. These patterns are not direct pictures of the waves themselves. Instead, they are fingerprints, surface signatures left by the internal wave's passage far below. The satellite does not see the underwater wave. It detects how the wave's currents reorganize the surface texture. This indirect method has allowed scientists to map internal wave activity across the globe, from the South China Sea to the Andaman Sea and beyond. By analyzing SAR images, researchers can pinpoint where internal waves are most energetic, track their movement, and plan shipboard campaigns to intercept them. The alternating slick and rough bands reveal not just the presence of internal waves, but also their size, speed, and direction. What once required luck and deep ocean instruments can now be tracked from orbit, turning the ocean's invisible skyscraper waves into a global phenomenon that can be followed in near real time. The Luzon Strait sits between Taiwan and the northern tip of the Philippines, its seafloor carved into two parallel ridges separated by a deep trough. Twice each day, the tidal pulse from the Pacific surges through this underwater corridor, pushing dense water back and forth across the ridges. The geometry of these submerged mountains is crucial. When the tidal flow meets the double ridge system, the energy does not simply pass over, it is transformed. The surface tide, uniform and broad, is forced to bend and tilt the ocean's density layers, generating powerful internal tides that radiate away as narrow beams. Measurements and models agree. The Luzon Strait converts more than 20 gigawatts of tidal energy, more than the output of a dozen nuclear power plants, into internal tides, making it the world's most efficient natural engine for these hidden waves. To unravel how this conversion happens, scientists launched the Internal Waves in Straits experiment, known as IWISE, a multi-institution project funded by the Office of Naval Research. Matthew Alford, then at the University of Washington, led teams that placed deep moorings across and downstream of the double ridges. These moorings carried strings of current meters, temperature and salinity loggers, and turbulence sensors, spanning from near the surface to the abyssal plain. Their job was to capture the birth of internal tides and track their transformation as they moved westward into the South China Sea. But the story did not end with fixed instruments. Spray underwater gliders, developed at Scripps and piloted by Alford's team, patrolled the water column from the surface down to 1,000 meters, cruising silently along the paths of the internal waves. These autonomous vehicles recorded profiles of temperature, salinity, and currents, filling in the gaps between moorings and catching the fine structure of the waves as they steepened and split into solitary packets. On the seafloor, pressure-inverted echo sounders, PIES, sat like patient sentinels, pinging sound pulses upward and listening for echoes. Shifts in the travel time revealed the slow, powerful vertical motion of the water column, mapping the rise and fall of density layers as internal tides passed overhead. In the laboratory, Thomas Peacock and his team at MIT built a scaled replica of the Luzon Strait in a giant rotating tank. By layering fluids of different densities and generating tidal currents, they watched as internal tides sprang to life, confirming that the double ridge geometry was the key to producing the enormous waves seen in the field. The combination of moorings, gliders, PIES, and laboratory models allowed scientists to trace the entire journey, from the initial surge of the barotropic tide, through its conversion to internal tides at the ridges, to the formation of ranked solitary waves marching west into the South China Sea. Every instrument, every model, pointed to the same conclusion. The Luzon Strait is not just a birthplace, but a factory for the ocean's largest internal waves. Some internal waves travel as single, steep crests, solitary waves that hold their shape for hours or even days as they move through the ocean's interior. In oceanography, these are called solitons. Unlike the rolling trains of surface waves seen at the beach, a soliton is a compact, isolated pulse. It forms when a powerful internal tide steepens and then breaks away from the main group, racing ahead as a distinct, self-contained wall of motion. The physics behind this lies in a delicate balance. Nonlinearity tries to sharpen the wave, while dispersion tries to spread it out. When those two forces are in equilibrium, the wave travels unchanged, sometimes for hundreds of kilometers. In the South China Sea, solitons can reach vertical displacements of 100 to 300 meters, with some extreme events pushing that even higher. These waves are not just tall, they are long. Their crests can extend for tens or hundreds of kilometers, forming immense underwater fronts that sweep across the basin. For a ship or submersible, crossing the path of a strong soliton can feel like hitting a moving wall. The water column shifts abruptly, bringing sudden changes in current and buoyancy that challenge both navigation and control. Not all internal waves share the same structure. Oceanographers describe these waves by their vertical modes. The most common, Mode 1, acts like a single broad bulge. The entire pycnocline lifts or drops together, moving much of the water column in one direction. These are the skyscraper waves that dominate the Luzon Strait and northern South China Sea. There are also Mode 2 waves, which behave more like a double-decker bus. In a Mode 2 wave, the mid-depth layer rises while both the surface and deep layers sink, or vice versa. This creates a stacked, opposing motion that can trap energy at certain depths and produce complex patterns of shear and mixing. Understanding these distinctions is more than academic. The mode and shape of an internal wave determine how it interacts with the seafloor, how it breaks, and how much turbulence it creates. They also set the stage for the most extreme events ever measured: solitary waves with vertical displacements of hundreds of meters and current speeds strong enough to reshape the local ocean environment. The vocabulary of soliton, Mode 1, and Mode 2 gives scientists the tools to describe and predict these hidden giants as they travel unseen beneath the waves. On December 4th, 2013, a mooring anchored on the continental slope of the northern South China Sea recorded one of the largest internal solitary waves ever measured in the open ocean. Instruments buried hundreds of meters below the surface registered a sudden, dramatic upheaval. A density layer inside the ocean shot upward and then plunged downward by nearly 240 meters. This vertical swing, roughly the height of a downtown skyscraper, unfolded in near silence at the surface. At the same moment, an acoustic Doppler current profiler, deep on the mooring line, detected a powerful westward surge. The current inside the wave's core reached 2.55 meters per second, fast enough to rival a strong river, yet entirely hidden from view. For comparison, most open ocean internal waves move water at a fraction of this speed. The instruments captured the full structure of the event: a steep, Mode 1 solitary wave, its energy focused along the density interface, racing toward the slope. The entire water column shifted as the wave passed from the thermocline to the deep layers below. This was not a model or a distant satellite signature. It was a direct minute-by-minute record from the heart of the wave. This December 4th event stands as a benchmark for just how extreme these underwater giants can become, with impacts felt from the seabed to the upper ocean, all while the sea above remained deceptively calm. As a giant internal wave approaches the continental slope, the rules of the ocean interior begin to change. The wave grows steeper, its energy squeezed upward as the seafloor rises beneath it. At a certain point, the smooth, ordered motion inside the wave collapses into chaos. Layers that once slid past each other with barely a ripple now overturn and mix, producing turbulence that is anything but subtle. Instruments in the South China Sea have measured turbulent energy during these breaking events that is 10,000 times higher than in the open ocean. This is not just a matter of numbers, because this mixing physically stirs heat, salt, and nutrients between layers that would otherwise remain separated for years. The result is a vertical conveyor belt. Cold, nutrient-rich water rises toward the sunlit surface, fueling plankton blooms and supporting coastal fisheries. At the same time, warm water and dissolved gases are carried downward, helping to ventilate the deep ocean. For those who work beneath the waves, these breaking events are more than a curiosity. Submarines and autonomous vehicles can encounter sudden shears, currents shifting speed and direction over just a few meters of depth. The density structure itself can change in minutes, altering buoyancy and trim. Even the speed of sound in water is affected, as temperature and salinity are scrambled by the mixing, leading to unpredictable acoustic conditions. What seems like a stable environment can turn hazardous in the wake of a breaking internal wave, with strong vertical and horizontal currents pushing equipment off course or even damaging sensitive instruments. In these moments, the ocean's hidden turbulence becomes a force to be reckoned with, not just for scientists, but for anyone operating in the deep. The term underwater tsunami often surfaces in news stories and online discussions, but it leads to confusion more than clarity. Tsunamis are surface gravity waves triggered by dramatic events like earthquakes or landslides, sending energy through the entire water column and producing visible, sometimes devastating surges at the sea surface. Internal waves, by contrast, are born from the gentle but persistent tug of tides and wind, traveling along invisible density boundaries deep within the ocean. Their power is real, hundreds of meters of vertical motion, currents strong enough to rival rivers, but the sea above remains calm, betraying almost no sign of the upheaval below. Some of the confusion comes from sonar and acoustic images. Submariners and ocean engineers have described moments when instruments register a sudden, steep wall of water or a sharp tilt in the thermocline with little or no warning. These episodes can feel like an encounter with a moving undersea barrier, leading to talk of walls of water or underwater tsunamis. In reality, these signatures most often reflect a passing internal wave, a vertical displacement of density layers, rather than a true tsunami. Occasionally, instrument artifacts or unrelated current fronts can mimic the same effect, adding to the myth. The distinction matters. Internal waves move energy and water inside the ocean, not at the surface. Their impact is profound, but their motion is fundamentally different from the surface surges of a tsunami. Recognizing this difference helps prevent confusion, and it brings the focus back to the real story. The ocean's largest waves are hidden from view, shaping the world beneath the waves in ways that are only now coming fully into focus. Right now, internal waves are shaping the ocean's climate engine, mixing heat, carbon, and nutrients in ways satellites only hint at. As climate shifts and undersea technology expands, understanding these hidden giants is not just science, it is a necessity. The greatest forces beneath our oceans remain largely unseen, but their impact is anything but invisible. What else moves beneath the surface waiting for us to notice?